to my mock recently, and they were like, "Oh yeah, I got it organized like this." I'm like, "Yeah, that's how we organize it." So obviously, information gets out, which is good. I mean, because if you know that, that's great. I mean, it shouldn't be a secret anyway. But you have your. We'll go over lift first, and then we'll go over drag. With drag, we'll do wingtip vortices. There's 5 areas in the PTS that we need to cover, right? So wingtip vortices. Then we'll do weight, and with weight, we'll do load factor. We will do thrust. We'll do the left turning tendencies, and then along with thrust. And then after we're done all those, we'll do controllability and stability. Wing design, I think, or attributes or something like that, it's described as, that gets covered with lift. So basically each one of these 5 concepts gets, 4 of them get worked into here, and the 5th one, stability, we just present at the end, after we have the 4 portions of flight done. So first thing is wing design. Good wing. What you want to make sure you're doing is you're labeling everything you draw. For sure. Kind of a bent line there. Make it a little straighter. There, it's a little better. Okay. So. To me, that's enough for airfoil design. I'm not talking about swept back wings and semi-tapered wings and these wings and those wings. It's more of like, what is the basic design characteristics of an airfoil? So I got wing design, come up here, draw a nice little wing, make sure everything's labeled, because a lot of times people draw something, I'm like, label it. And the people who you're presenting this to in the DPE, and when I'm in there in the mock, I basically try to empty my brain, like, okay, if I'm a student that doesn't know anything and you're presenting this to me, am I going to understand your lesson based on having no previous knowledge of this? So you have to label everything. So leading edge, trailing edge, chord line. I just mentioned that that's an imaginary line that connects the leading edge to the trailing edge. The upper camber is that curvature of the upper part of our wing. And the lower camber, which is this flatter portion, is on the bottom of our wing. The air, as it comes in contact with our wing, it flows above and below the wing, and this is called the relative wind. It's the wind which is directly opposed to our relative path. that's it for wing design. Then get into lift theory. So I'll go from there into lift. Two theories. And so, Bernoulli. So Bernoulli was a scientist, is our first theory of lift, Bernoullian lift theory. And so what he found out was he was working with these things called Venturis, which Venturis are nothing more than a tube with a constriction in the middle of them. And he was able to measure, quantify the velocity of the fluid moving through this tube. He was able to measure that, as well as he also was able to measure the pressure as it traveled through this tube at the same time. And he found a pretty cool relationship with these two things. What he found was, as right here sort of in the constriction, this is the big part here. Kind of the aha, which is, if we increase the velocity of a fluid, the pressure decreases. So what happens is, in order for this fluid, there's a large mass of fluid that's constantly putting through here. In order for all those molecules to get through that smaller space, they need to speed up to all fit through that smaller space, right? And as they do that, the pressure of the overall fluid ends up decreasing because of this acceleration of the molecules that going through this constriction. And so from Bernoulli, we have basically as velocity increases, pressure decreases. So if we take this little bit out here, and we kind of just, if we made that sort of solid along the bottom here, this constriction looks a lot like our wing. So that, draw another wing here. Okay. And so we have that air, which is also a fluid. Air acts as a fluid. Coming in and hitting our wing. We have a point right here on the front of the wing, called a stagnation point. That's where all the air sort of hits and gets collected momentarily, kind of abruptly gets compressed in that area right on the leading edge of our wing, before it it gets split into two airflows. Some of the air gets displaced and ends up moving over top of the wing, kind of like that diagram above there, and some of it moves relatively straight underneath the bottom of our wing. So if we look at this, we can see top of our wing displaces a lot more air and sort of protrudes into the wind more like this venturi here. So what it's doing is air's getting that compression on the top as it goes over the top of the wing. The distance also on the top of the wing is greater because our upper camber is a lot bigger than our lower camber on our wing. And so what happens is this air that gets compressed because of the increased distance it needs to go over the top of the wing, it needs to speed up, just like in the venturi. So if we have the velocity increasing over the top of the wing, the pressure is going to decrease. Okay, and what that's going to do is that's going to cause a relative low pressure on the top of the wing because of that increased velocity. Then compared to the bottom of the wing, which will have a relatively high pressure underneath the wing. Now, one thing we know about high and low pressure, you may have studied it in weather, but everything moves from high to low pressure. And the easy way to think about this is everybody's been to a party, and so if I blow up helium or even just a balloon, or I'm floating a helium balloon there, and we have high pressure inside the balloon, relative to the pressure inside the balloon, outside we have just regular air, so relatively low pressure outside of the balloon. And if I were to open this up or cut this off the bottom there, so I could open that up, okay, all the molecules, all the high pressure molecules that are in here are going to want to rush out and escape, right? If we pop the balloon, it would actually just pop and forcefully equalize itself. But the high pressure is going to empty itself into the low pressure until air equalizes itself, right? Fluid's going to want to equalize itself between the high and low pressure. Chad, did you want to teach principles of flight? Here you go.
Yeah, I've been listening. No, for no reason. I was chasing them.
You got any more spin flights?
No, not today.
Okay.
Not today. Some of you guys tomorrow, right? Who's tomorrow? 2, 3, 4, 5. All right.
I swear I'm gonna take this thing down. I'm just gonna unplug this for now because I can see something bad happening. So yeah, so I like the balloon party example. So then basically from here, what you're saying is, okay, so we know that from here, that high seeks or will always move towards low pressure, right? That's something we can deduce from that example. And anybody in their mind, or student, any of them have all been to a birthday party, they all know what a balloon's like, and yeah, it deflates, high pressure goes to moves to low pressure. Well, the same thing happens with our wing. As we're moving through the air, we have this relatively high pressure underneath, and what happens is it's trying to get to the low pressure. Problem is, there's this darn wing in the way. So what happens is it ends up pushing up on our wing, and the high pressure trying to get to the low pressure, and therefore creating lift. Okay, so that's how I do Bernoulli. Okay, and I use the balloon example to kind of bridge that. I guess I'll have to do another board for Newton. If anybody wants to take pictures of the boards as I go along, that's fine, if you're taking notes. So, okay, cool. All right. second theory of lift is going to be Newton. Second theory of lift is Newton. Third law. Okay. And Newton's third law states that for every action there's an equal and opposite reaction. Okay. So draw another wing.
Not really. You might use that up.
Okay, so we have the wing there, and we have, let's see here. We have the chord line. So put the chord line back in there. And so it's relative wind. So if we were to extend this chord line out, it should be more like this.
I don't think that cord line's straight enough, Charles.
I know. You see that? I kind of went, eh. I know. See if I can get it more. Something like that. Just kind of more like that. Okay. So we have the relative wind. Got the chord line. So once you write this stuff once, you can abbreviate it. But write the word out completely the first time you introduce the concept. And so here you might see me introducing abbreviations with writing out full words, because anything new that's gonna come out, I'm gonna write it up. Anything we've already discussed, I'm gonna abbreviate. So we have something, a new concept here we need to talk about, and that is something known as the angle of attack. What is the angle of attack? So AOA. So AOA is the angle between chord line and the relative wind. And so when we're flying, our wing is not directly at, our wing always has a slight pitch up typically, even on, we have an angle of incidence, which we're not gonna get into, right? We can talk about that if you wanted to get into that, how it's actually formed on the plane. So we have this angle of attack. And so what happens here is, you know, our wing, sometimes we're pitched up, we're pitched down. In this case, we're talking about when we're gonna start pitching the wing in upward direction or positive pitch. What happens is this underside of our wing, that was a horrible wing there. Okay. Gets more and more exposed, the undersurface of our wing gets more and more exposed to, still not straight, the pole or something. Gets more and more exposed to the relative wind. That sounds cool. Sounds expensive. Alright. So again, angle of attack, relative wind. Right, and there's the chord line again. So, a couple things about this. Before I get into really trying to explain this to somebody, is what most people don't understand is they think that if you tilt the wing up, your student thinks you're flying and the relative wind is still directly onto the wing most of the time, okay? They don't understand this. So this is something where you need to bring in. So let's talk a little bit more about this angle of attack, but also I want to talk about the relative wind a little bit more for a minute here to understand exactly how it's interacting with our airfoil, okay? So, you guys have probably all ridden bicycles before. And so, if I'm riding a bicycle, definitely not an artist, but we're riding a bicycle, okay? And we're moving in this direction, okay? You'll feel a breeze in your face as you're riding that bike, or even if I'm walking at a brisk pace, I kind of feel the air, if it's cool or maybe a hot day, I kind of feel the air moving around me. That's my relative wind as I'm moving through the air. So as long as I have just riding the bike, the relative wind is directly head on to me, right? But now I can't leave the ground on the bike, but I can pop a wheelie. So I start doing some fun little stunts because I'm bored just riding it around and I want to do some fun things. So I'm still moving in the same direction though. My positioning has changed, but the actual direction in which I'm moving is still straight along the ground. So the relative wind is still coming from the same direction. The relative wind is not coming from here. Not unless we were actually able to just take off like, you know, on a bicycle, right? So the relative wind is still directly at us, but now there's an angle, right, that's formed between us and that relative wind, okay? That would be like, or equivalent to what I'm talking about here is the angle of attack. So when we're flying, talking about flying straight and level, and sometimes as we slow down, right, we need to increase that angle of attack, but we're still flying straight and level. So the relative wind is still coming horizontally directly at our airfoil, which is the situation here, the way I drew it. But this analogy here, a bicycle, usually, a lot of times you'll see like a light bulb click on when you draw that, because they'll be looking at you like, I have no idea what you're talking about. And then you draw that like, oh, okay, that makes sense. So you see these aha moments in your student's eyes. So we have that. So that is our angle of attack. Now, the one thing that's cool is, like I say, Newton's third law, which is, normally I would write it out, but for every action, there's equal and opposite reaction. So, if the wind's hitting the bottom of the wing and getting deflected downward, getting pushed downward, the wind is pushing back, or the air is pushing back on our wing and pushes our wing the opposite direction, upward. Great example of this is basically just taking your hand, right? And if you're driving down the road at 50 miles an hour or so, and you stick it out the car window, roll it down, stick it out, and just tilt your hand. Now my hand's not an airfoil, but if I relax all the muscles in my arm, I guarantee you my arm is gonna get pushed up and it's gonna be sitting up here like this at the top of the window, right? So it's that relative wind that's striking the bottom of my hand. My hand's pushing that air down, and therefore it's pushing my hand up, even though my hand has no way to create lift. As an airfoil, the principle still works, the action-reaction, right? So the more we pitch, okay, so this would be, so we create an angle of attack by pitching, right? So this would be a pitch movement, where we'd be pitching the aircraft up, but we're still flying. Our movement is still in that same direction. We're getting additional lift from this air striking the bottom of the wing, just like the air would strike the bottom of our hand. So something we can walk away from this with is, okay, so if I increase my angle of attack, it generates more lift. So from Bernoulli, we have increased velocity, increased lift. That would be his theory, right? We walk right there, velocity going over. And for Newton's third law, we have increased angle of attack, increased lift. So, pretty cool. Sounds great. Let's just keep doing it then. If I want more lift, easy enough. More angle of attack, right? More lift, more angle of attack. So, but at some point, there's the law of diminishing returns comes into play here. And so, maybe you guys have been to maybe Bushkill Falls in Pennsylvania, maybe some of you were lucky enough to go to Hawaii, see some beautiful ones there. But I'm sure you guys have probably seen waterfalls before, right? At least on TV. Not really. Okay. So this water is moving at a great speed, right? And if you've ever seen a waterfall, the cool thing about a waterfall is it kind of goes out and it leaves there's like the cliff that's behind it. So if you waterfalls, I mean, even the ones in Pennsylvania that aren't even that big, you can kind of like walk up to them, you can walk behind them, right? You can walk behind the water's like going down in front of you. So why is that? Well, at a certain point or a certain angle, okay, whatever that angle is, the water, because of its velocity and how fast it's moving, it wants to stick to the ground. Gravity wants to keep it stuck to the ground. But because this angle, this cliff, is at basically a 90-degree drop, we're very close to it, the water cannot do that. It can't just sit there and fall straight down, right? So it ends up going off the cliff and separating. Okay, so we have separation of flow of the water from the ground. Okay. Now, if maybe the angle wasn't so steep, you know, we just had a steep grade, 40-degree angle or something like that, the water would just keep flowing right down it, right? But at some point, it gets to an angle that for however fast this water's flowing, it can't do that, and it causes a flow of separation. So, taking that there and bringing that into our model here is we have that relative wind, and now we're getting all kinds of crazy deflection off the bottom of this wing, okay? But at some point, this air we get a separation given angle. So we got that chord line, got the relative wind, and we now have this large angle here, and so we have something, a concept here called the critical angle of attack. critical angle of attack is the angle at which laminar flow, air separation from top of the wing occurs destroying left. So here, right here, in this area here, we can see it right here. So we have laminar flow separation. So normally the air is stuck to our wing. Think of like laminate. You know, anything laminated. This table's laminated, it's stuck to it, it's stuck directly to the surface, laminate. Laminar flow, the air, once we reach that a certain angle known as the critical angle of attack, just like in this waterfall, the air, just like the water, can no longer stick to the surface. So we have separation over the top, starts at the trailing edge and works its way forward, okay, the separation. And the air starts to burble and eddy, and that is actual FAA technical verbology. I wonder if Ernie would agree with that. Burble and eddy. But those are the terms.
If you can find it in a book.
If I can find it in a book, then it's good, right? So we have this laminar airflow destroying all lift at this critical angle of attack. So good news, we can get more lift with greater angle of attack. Bad news, we can only get it to a certain point, right? Now, a wing will always stall at the same critical angle of attack, regardless of airspeed, attitude, anything. If you exceed the critical angle of attack of the wing, it will stall. Okay? That's something you need to emphasize that you know, right? FAA written test question and everything, they want your private pilots to know that too, right? All right, so those are my two boards on lift. Anything you want to take notes of or pictures of there? I raced my bicycle guy on you, but if you guys have anything you want me to, like, critique, fill in, maybe add something, let me know. I don't see any hands. All right.
I have a question.
Yes.
So during our grounds, the Zoom classes, our instructor was talking about the bicycle method, the same thing that you were mentioning.
Yeah.
But he also threw in there the constant climbs with the relative wind as well. Do you think that would be a good idea to keep those in, or
Constant
this-
climb.
or like a straight climb and where the relative wind is compared to the climb?
Yeah, so I don't want to, in the principal flight, I don't want to confuse the student
Okay.
too much, you know what I mean?
Yeah.
Because then they'll be like, well, he's telling me it's coming this way, but then at climbing it's coming this.
Yeah. Okay.
So, it depends on your student too. You got someone who's really bright, science background, they're like, they get it. You could probably roll right into that.
Okay.
Otherwise, I would save that lesson. I would do this lesson, and then I would save that. Be like, hey, remember when I told you about the relative wind and da-da-da and this and that? Well,
Here it is again.
here it is again, but it's different now because da-da-da-da-da-da-da, right?
Yeah.
Explain that to them. And by having that separation between the two lessons, I think it better cements it in their head, whether if you try and give it to them all in one lesson,
Okay.
it can be confusing.
Maybe a little
It's-
too much information.
It can be a little bit too much information, yeah, that there's
Okay.
too much to select from, I think.
Okay. Cool, thank you.
Sure. All right, cool. All right, we'll erase this. So we talked about lift. And now we're gonna talk about drag. Okay, two types. We got parasite. And induced. Parasite has skin, form, interference, okay, and induce, just as induced, okay? It's just, byproduct of lift. That's all we got for induced. All right, so the first one is parasite. And skin friction. And so, let's see here, we took away a piece. And usually what I do is I'm just squiggling my marker back and forth real gentle, and that's kind of creating like what looks like a little bit of bumps, okay? So this is the skin of our airplane. Okay, just a sample, any piece, doesn't matter if it's on the nose, wing, wherever, right? Anywhere on the plane. And for the most part, if we feel the fuselage or any part of the metal that's on that plane feels relatively smooth, it's painted, it has a nice finish to it. But regardless, no matter what happens is we have air that's moving past our plane, and at the, what I call boundary layer, which is the layer that is right, just separating the air molecules from the skin, right, where they're in contact with one another, right? We have friction, air friction. Only way to escape it would be to do like Elon Musk did and, you know, shoot a Tesla into outer space, right? That doesn't have any skin friction on it. It's vacuum. So we would need to be operating in a vacuum in order to get rid of skin friction. So it doesn't matter if you're moving your car, any object, even yourself, everything moving through the air has skin friction at its boundary layer. The air molecules basically interact with that layer, and no matter how smooth the surface seems, there's always microscopic imperfections in that, which is going to bind and grab with the air molecules slightly. And that's going to cause, let's say, a type of drag, which is the friction, which is literally just the air that's kind of grabbing onto the skin of the plane as it's sliding across it as we move through the air. Just so, for those of you who, this is not part of the lesson. Okay, so it'll be like, this would be at like 30,000 feet. You're flying a jet at 30,000 feet, and you're flying at, 600 miles an hour basically, Mach 0.82. You'll see that on your gauges, one of the things on one of your multifunction displays, typically it will display these two numbers. And the SAT is the basically just the standard air temperature. What is the relative air temperature outside? So about 32,000 feet, everything, all the time, all times of the year, it's -50. We're very close there to it on a semi-standard day. So it's always right around -50. But as we're going to Mach 0.82, we have another temperature that's 8 degrees warmer. And that's our total air temperature. And that's the actual, they have a probe on the plane that actually measures the temperature of the skin of the plane. So when you say is there skin friction, well, there's enough skin friction, air, when there's almost no air up at that altitude, to warm the outside of the plane up by 8 degrees Celsius by moving that fast through the air. The skin friction in and of itself warms the jet's skin up. Now, not that much, but still, right? So that's one of the things when I started flying for the airlines, I was like, oh, skin friction. I was like, but this is like, you can actually see it, like this is it, like happening right in front of your eyes. So obviously we can't get our Cessnas to go that fast to cause that to happen, but yeah, at relatively high speeds, you know, it actually will cause a rise or an increase in temperature even from that air skin friction going over the skin. Okay, so skin, and then we have form, drag. Okay, so form. So form drag literally is the shape of the object, and form drag can be measured relatively by air displacement. So it can be thought of as that. So the more air an object displaces as it moves through, okay, the environment or through the air, the more form drag it has. Now our aircraft, just like any aerodynamic thing, we want, just like boats, they want to be have the least amount of friction as well. You know, they're formed and designed in a certain manner to minimize this type of friction, to minimize form drag, right? We don't want to go fly a flying brick. We want something that's aerodynamic, that's going to go fast. It's going to cause us the least amount of drag as we go through the air. So most of the surfaces on our aircraft are curved or molded, or so that the skinny piece is kind of, you know, facing forward. The biggest piece we have is our cowling out the front, which is relatively flat, still curved, but relatively flat, which causes a lot of form drag, as well as our windscreen. Anything that opposes the relative wind or exposed to the relative wind, that's what's going to cause your form drag. All right. So form drag in of itself, what I always try and compare it to is, like I say, it's displacement of air. Okay, and it's the shape of the object as it moves through, and so really bad on this one. So a couple of stacks that one, but there you go. Something like that, like a bus or whatever, something like that, versus like, you know, have like a little, it looks like a wing almost, but yeah.
Like a raindrop versus
You
a
know,
snowflake.
like a smaller car versus a you know, big orange or yellow school bus. That's, you know, those ones that are like flat in the front, or like the old Mack trucks. You know, they're going to displace a lot of air. The other thing I do sometimes, I'll say, hey, if I have a notebook or anything, I'll say, you know, form drag, what does that look like? Well, you know, if I take this piece of paper, the most aerodynamic way I can push this paper through the air would be this way. Why? Well, it would have the least amount of form drag. Why? Well, because to the relative wind, I have the least amount of exposure. I only have about a half an inch of thickness of exposure on this piece of paper. If I turn the piece of paper up and try and move it this way, right? You guys won't feel a breeze if I do this enough, right? It's going to displace a lot of air, right? To move this whole thing 8 by 11 through the air, I can even feel the wind resistance on this as I just even move it gently through the air. It has a lot more form drag on it because it's displacing a lot of air around it. So we can't really do anything about these types of drag. It just is what it is. And again, this has to do with how our aircraft's designed. Engineers, again, designed it with aerodynamics in mind to minimize form drag. But no matter what, there are still surfaces that are exposed to the relative wind, and we're going to have some form drag from our aircraft as it moves through the air. Last type of parasite drag is interference drag. And interference maybe I'll draw that in a different color. So if these are two rivers, right, and we had two tributaries coming together to form a bigger stream or bigger river, the point at which those two intersect, they're going to be going at their own different velocities. You know, they're going to have their own relative velocity. They're also going to have their own relative direction. And when they come together at this point right here, we can expect when they mix together that one, we might encounter some rapids, right? And two, the water is going to be very turbulent. Why? Because these two streams of water are coming together and mixing together. They're slamming together, getting forced together. And again, one's trying to go one direction, one's trying to go the other. They get forced together. Same thing happens in our plane. So typically it's around places that have connection points. I sort of like this one the best for an example. Here. Something to that effect. Here we go. Okay. So interference drag occurs when two streams of air that are operating in different velocities, different directions, come together and meet. And so one thing, we have certain air going over the top of our wing, and we have air going over or down the side of our fuselage. Right, and we know you can say, well, doesn't it? Don't we have the spiraling accelerated slipstream, and it doesn't really go down the side of our fuselage at its width? Yeah, you're right. Okay, but for this example, it goes down the side of our fuselage. Okay, so so the air coming over the top of the wing kind of comes after it gets done with the wing, comes crashing down like this. Air slipping down the side of our fuselage kind of comes in and hits there, and then it's the point past the wing where it meets the body. And a lot of times you'll see, like in your drawings or on the BIAC, it'll show you like where the wing meets the body, right? And things like that. Like it's in those connection points, which is where this occurs. And I drew it a little further back, but it's, you know, it's basically right in here where those two streams right past the wing would meet, right? Would be a point of interference drag. So, yeah, so we have connection points like that all over the aircraft. We have interference drag. That's just one of the best examples, areas that I like to draw. And I think it's easier to draw it with a Cessna than an Archer, so use Archer folks. I mean, I know you love your Archers, but you might wanna draw a Cessna just once. I don't know, it looks easier, you know, because obviously on the Archer, you know, if the wing's down here, this is coming down here, there's no drag, so you gotta come up with a different point, or you gotta draw it a different way. You gotta draw it from top down or something like that. With the Cessna, you can draw it in a profile view and show it. Okay. Any questions about parasite drag? So you see, I'm not going really deep, you know, and I'm not getting complicated. I'm not getting into all these other, you know, tangents and things. I'm just keeping it very simple. But I'm explaining what each thing is completely. You should be able to walk away and tell me what skin friction is, or you should be able, I should, you know, have a student walk away and tell me what form drag is, you know. Okay. So, induced drag. Byproduct of lift. Yeah. You guys are done CFI CAD, you guys should be experts at drawing wings. Draw them all the time, right? At least if you're doing these type of lessons, you do. Okay. So, all right. Yeah, I think I used green before, so we'll stick with green. Let's do this. So we'll do. So phone's running out. So, one of the first things to draw on induced drag is just draw the wing again. And basically we have our relative wind, and then we have here, which kind of comes down here, and kind of gets in, and this is what we call the local flow. You want to get technical with that. Downwash. So basically, as our airfoil is creating lift and this laminar flow is going over and underneath our wing, this, we said that the air above the wing has a low pressure, but it also has a much higher velocity. That's why it has a lower pressure up there. Well, that air comes streaming off the top of that wing and comes slamming into the air that's just kind of slipping underneath the wing, and actually ends up redirecting the flow of air, kind of creating its own relative wind, and this is called the local flow. okay, known as a downwash. And it's this disturbance of air that causes this burbling and drag off the trailing edge of the wing. In fact, so much that our lift vector, which is typically perpendicular, ends up getting pulled, and this is exaggerated for illustration purposes, probably should be right next to it, but it is slightly pulled back, and is the difference between the lift vector where it would be perpendicular to where it gets slightly pulled back is our measurement of what's considered induced drag, and that's the drag that's literally formed by the airfoil, by the wing itself. Induced drag is not formed anywhere else but by the wing. So it has the wing special, it has its own special drag named for it and everything, right? We love our wings. So, now on top of that, this is sort of looking away. And yes, it does matter which way you draw these. You can draw these incorrectly. So they should go down and then kind of circle back up towards the wing on each side, right? So these are, so there's something else in here. So all along, course of our wing, we have this high pressure that's trying to get to the relative low pressure, which is creating that lift for us. And it can't get there, except out of the very, very tips of our wings, it says, aha, I found a way to the low pressure. And so what it does is it actually creates air slipping off from underneath our wings here, as it's underneath the wing, and it makes it want to go out and try and seek this low pressure. And when it does that, it tries to seek the low pressure that's on top of our wing. But the problem is by the time it gets there, we're already gone. So this ends up falling behind the aircraft and spiraling down, out, and away. So these move down, out, and away. Okay, for the most part. And they do that at a rate, they fall at a rate of 500 to 1,000 feet per minute. And this is also part of wingtip vortices are also, the reason I'm putting it here is because it's also part of induced drag. So we have the downwash, we have the wingtip vortices, right? So these two factors coming off of the wing is what's causing us our induced drag, all right? So furthermore, what FAA wants us to know is that wingtip vortices are hazardous. They're hazardous to our health. They could cause us to crash if we're not aware of their behavior and how they act and how to avoid them. So we're gonna talk about that next. Anybody want a picture? Because I'm gonna erase all that so I can get room to do a whole wingtip vortice board. Okay. Let's just get over all that. We'll just do this. So, So we have that, and I had the down, out, and away. Negative 500, 2,000 feet per minute. Okay. And what's my next one on this one? Oh, okay. So wingtip vortices are formed, they are formed from induced drag. They are a byproduct of lift, right? So since they're a byproduct of lift, like we said, from induced drag, if we have, the more lift we have, the more wingtip vortices are developed. In fact, actually, the heavier the aircraft, right? The more gross weight, it requires more lift, which also increases wingtip vortices. So we're worried about whatever that means, start. We're worried about big planes, right? So I'm not worried about a fellow 172 that I'm flying behind. Will I catch some wingtip vortices off of them? Yeah. But are they gonna do anything to me? No, probably not, right? Just maybe annoying. But we're looking after, the concern with wingtip vortices is the bigger planes with heavier gross weights. So those things, even a business jet, Gulfstream, any regional jets, airline jets, cargo jets, right? Big planes. So the wingtip vortices are dangerous when they're creating the most lift. And when are we creating the most lift? Well, FAA wants you to know that wingtip vortices are at its highest because it's when we're creating most lift. Well, we need to create most lift when we're heavy. Clean, because it allows the wingtip vortices, the actual air, to flow out undisturbed and actually create these rotor clouds. So clean. And since we are creating that, again, we're creating the max amount of lift, typically that means we're at a high angle of attack. And if we're at a high angle of attack, we're flying slow, right? So heavy, clean, and slow is the condition in which we want to be worried about the most. So when would that be? Well, that would be most likely when the airplane or the jet is taking off. So at takeoff, and also we're worried about it when we're coming into land and we're relatively slow. So takeoff and landing are the two times in which we're worried about these wingtip vortices the most. And again, if this is the flight path of our jet, we know that the wingtip vortices are falling down underneath their flight path. So this area down here, underneath there, is a no-go region. That's a dangerous area. We don't want to be there, right? So how do we avoid? So wingtip had one just today with Addison. We were over at at Cecil, brought in a P3 for a touch and go, you know? I think it was a P3, I don't know, maybe it was one of the big military jets. So I'm just like, all right, it's all smoke. Second stripe after the 1,000 footers, aim for the fourth stripe. You know, it's a 2 mile runway over there, so we could land and take off a couple times with the Cessna. So not a big deal, but you know, we were doing this exact thing today, as we were over there. So what do we wanna do? We wanna stay above, the other aircraft's flight path. Right, so stay above in the flight path for us. So this is our little trainer. Okay, we want to stay above. Touchdown beyond. Rotate before. And obviously we're gonna rotate long before that, so we'll rotate like there. So, and stay above. So I hear a lot of people call this the bowl method. I don't know, I've been hearing that a lot lately, so I've never heard that before, but yeah, it looks like a bowl, it's like a bowl inside of a bowl. So basically you're doing this, you're premising it with what are wingtip vortices, why are they dangerous, what are we concerned about for? Well, it's again, the bigger planes, the heavier weights. When are we concerned about it? Heavy, clean, and slow. Well, that's typically when we're taking off and landing. So how do we avoid them when we're taking off and landing? Stay above, you know, fly the bolt, stay above, touchdown beyond, rotate before, climb above. And if you can't climb above, then after you rotate, you get to a safe altitude, sidestep to the upwind position. So if you got 30 degrees coming off your right, do a sidestep, climb out to your right, because the wind's gonna blow the vortices the other way. So landing and taking off is the most critical time for these, and something else the FAA wants you to know is there is the most is a most hazardous conditions time, and this is if we're ever taking off, which you should not be, but sometimes you do, you and your Craig, because they're crazy. Is with a light quartering tailwind. So So if we're taking off behind a large jet and we have a light quartering tailwind, what's going to happen is we said the wingtip vortices like to move down, out, and away from the aircraft. Fortunately, with a light quartering tailwind, it will blow the downwind wingtip vortice further away from the runway, but the upwind vortice will be held over the runway the entire time by that light quartering tailwind. Instead of being able to dissipate out and away, it's actually going to hold that light quartering tailwind is actually going to sit there and hold it over the runway. So it's going to dissipate over the runway. So in this case, we wait our, what was it, 3 to 5 minutes or something like that, I think is what the PHAC recommends. So we gotta, in this case, we can't do anything but wait. We can't take off, the wingtip vortices are there, we can't destroy them. We just basically have to wait it out. So basically start a timer, and after the aircraft takes off, we wait for some time there, a couple minutes, to allow those wingtip vortices to dissipate over the runway before we go ahead and take the runway and depart. Okay. And I think that's about all I got for wingtip vortices. Any questions about that?
How would you describe the heavy, clean, slow? Obviously heavy because heavier aircraft needs more lift.
Need more lift.
Clean, what would you say for that specifically?
So the clean, basically is, so these wingtip vortices, what they're doing is, because it's trying to get to the high pressure air, I kind of drew the arrows where it's straight. The airflow is actually trying to make its way out to the wing, because it is bleeding off the wingtips. There is a slight relative flow towards those wingtips. So what happens is if I have flaps down or anything like that, it's going to disturb, it's not going to allow that
More form.
to form as strong as if it was able to cleanly just slip along a flat wing.
Got it. Appreciate it. Thank you.
Sure.
I can show you a video about that too.
Alright, so wingtip vortices. Drag. Alright, next one. So 8. So wait. Okay, so. So weight is the force that opposes lift. One thing I like to throw in there right away, because I know you're going to want to get into talking about G's, but you have to define what a G is. So weight, we know, is formed by gravity. Gravity is our constant. So any object that is experiencing its weight because of gravity by itself is considered 1G, okay, in our terms. So we're gonna just think of gravity, just to get rid of the whole word, and we're just gonna call gravity G. It's like an abbreviation for gravity, okay? So this is 1G. The normal weight of the aircraft as it's sitting on the ground. A couple quick things, obviously. In straight and level, lift equals weight. So therefore, if our plane weighs 2,000 pounds because of gravity, we have to be generating 2,000 pound units, if you will, of lift in order for it to fly straight level. Climb, obviously, lift exceeds weight, and descends, lift needs to be less than weight so that the aircraft actually will descend back to the ground. relatively easy concepts to understand. We talked about how lift is generated, but one thing we haven't talked about yet is what happens when we bank our aircraft, okay, with regard to lift and weight, because something special happens. You know, right now when we're in straight level, when we're flying level with our wings level, all of our lift is pointing straight up and all of our weight is pointing straight down. So it's relatively easy to understand, but we take our plane and we throw it into a bank. Now all of a sudden, we have weight, which is still from gravity. Another force here. And then we have resultant force here. We have this guy here, this guy here, and so we have So I think I should probably do another example real quick here. I'll pull one up right here. So. This is total lift. And this is total lift. Okay. So I think the first thing is to go draw just a nice diagram. I kind of mentioned over here, but you know, if I draw and I'm drawing my stick planes, you know, I'm such a great artist. 2,000 pounds of lift, you know, if I have 2,000 pounds of weight and we're straight, and this is, example is, you know, straight and level. Then if I have 2,000 pounds of weight, then I need to have 2,000 pounds of total lift. And what I'm gonna do is I'm gonna use those numbers to explain what happens when we bank an aircraft. Okay, so this is our lift. Okay, so from our example over there, and not that you have to use numbers, you can do this lesson without using numbers, but I just find that sometimes it makes it a little more concrete when you do use numbers that are relatively close to the numbers you're used to seeing on a daily basis. So one thing we have here is our aircraft gets banked, or we bank an aircraft into a turn. So what turns our aircraft? Well, lift turns our aircraft. Okay, we actually give up, when we bank our aircraft, you know, when we're straight and level, 100% of our lift is vertical. It's all vertical lift. Okay. We have to trade and give away some of our vertical lift and trade it for horizontal lift. Okay. And so this is so we can, turn, so we can actually turn the aircraft while we're banked, okay? So, let's just say, for example, we had 2,000 pounds of lift up there, but we had to give 500 pounds of that lift from our vertical component to our horizontal component to pull us through this turn. Okay. So right now, if we did that and we didn't change anything else, we're only left with 1,500 pounds of vertical lift. So right away we can see when we bank an aircraft, we lose a vertical component of lift. If we don't have enough lift to support the weight, our aircraft's gonna descend. It's gonna start a descent, right? Just like here. So in this case, lift, vertical lift, if you will, would be less than weight. So we're gonna have a descent. But just like in Newton's third law, for every action, there's an equal and opposite reaction, okay? So we split our lift component up into vertical lift and horizontal lift. And now we have a couple things going on here too. We don't just have weight, we have a force that's opposing our horizontal lift. And that is centrifugal force. Okay? And so that centrifugal force, like I say, is a counteract. It's an opposite and equal force. So if we're creating 500 pounds of horizontal lift, in essence, we're also then creating the opposite reaction would be 500 pounds of centrifugal force. So if we take this force, which is on, if you think about this as the wings is our dividing line, everything that's below the line, below the aircraft is fighting everything that's above the aircraft there, the lift components. You know, we have an imbalance right now. So I have a couple things to define for you. I have to define what centrifugal force really is. And we have another new term, load factor. So centrifugal force. What is this force and why is it felt in this direction? Well, what I usually do is I use the example of a person and they have a ball on like a chain and it's a 5-pound ball. And I start whirling that ball around in a circle. But because of the velocity, I'm spinning this ball, I'm turning, it's turning or banking, if you will. It feels like 15 pounds. Well, why does it feel heavier on the string than if I just stop spinning it and I weigh it, it's 5 pounds. It didn't change weight, right? The weight is the weight of the ball. So the ball's 5 pounds. So at any moment in time, this ball wants to continue on its path straight from inertia. But we keep redirecting this ball around into a circle. When we do that, the ball wants to pull away. And it pulls away with a force. And that force, so it wants to pull away, pull out of our hands, right? And so you have to hold on to the ball tighter and tighter, or the rope tighter and tighter, the faster you swing the ball. And that pulling away is centrifugal force, which is what you're generating as you're spinning that ball with that chain around your head. Same thing with the plane. Plane's being pulled to the inside of a turn. It doesn't want to do that. It wants to keep going straight. So the force that's opposing that turn and that's causing this to feel heavier is centrifugal force. So we have a new term, which is load factor. And what is load factor? Well, load factor is nothing more than weight plus centrifugal force. So in this case, that would equal, so load factor in this case is going to equal weight, 2,000 pounds, plus our 500 pounds of centrifugal force. Our load factor is going to be 2,500 pounds. What's that mean? So this is 2,500 pounds. This you can think of, it's a force. That's why I'm putting it in quotation marks. But you can sort of think of this theoretically, load factor as your total weight when you're in a turn. I say that, like I say, with quotation marks, because it's a force, right? It's not weight. But when we take the weight of the aircraft and we add our centrifugal force, we get load factor, or the total weight. So we add these two things together. And we come up with 2,500 pounds of force in this turn. If we do nothing else, we also have total lift, right? Well, what is total lift? Total lift is nothing more than vertical lift plus horizontal lift. Okay, that's total lift. And in this case, if we add those things together, we still only have 2,000 pounds. So we're 500 pounds short of being able to stay straight and level. So in order to compensate for this additional loading that's going on the aircraft, we have to somehow create additional lift. So if I have 2,500 pounds, I need my total lift to equal my load factor, right? That's what we want. How am I going to do that? Well, I need to increase this right here, my total lift. How do I do that? Well, how do we increase lift? Well, we figured out two ways. Bernoulli said we can do it with velocity, and Newton said we can do it by increasing our angle of attack. Okay, so if we're doing this at cruise and we do these maneuvers, turns typically at a cruising speed, we just turn, right? We typically don't have a lot more speed to go. Maybe we can add a little bit of throttle to it, but normally velocity, at least in these scenarios, is not going to be the answer. So we need to increase our angle of attack. And what does that mean? That means we need to increase our attack. To our students, that means to pull back, right? Or back pressure on the yoke. Increase that angle of attack. Bring that nose up a little higher on the horizon, right? Well, how much? Well, enough so that the lift increases enough to equal our load factor now. So how much would we need? We'd need to pull back. We'd need to increase our angle of attack to add 500 pounds of lift. And if we did that, equation we balance, we'll do a normal level turn, right? So there's a little chart. You guys might be able to help me out with this, what it is exactly. I think it's like 80, 70, there's 60 and then 45, something like that.
Yeah.
Is it 1.4? I know this is
Yes.
2, obviously.
Yeah, it's
1.4, 2, this one's 3, I think.
It's 4.5 at 80.
Which one is this one?
4.5 at 80.
The 4.5 at 80. Oh, at 80, right? Yeah. But at 70, I think it's 3. Okay. So so this would be our load factor, right? And this would be our bank angle. Okay. So once you kind of have the theory of that explained, done, and it's like, hey, well, you know what? We actually have a load factor chart that's in the books, and we know that at different bank angles, we have, or it's not load factor, well, it is load factor, but we express it in G's, right? So, our load factor expressed in G's. So, what does this mean? We know that if we bank our aircraft over, we will have to increase our angle of attack such that we will experience 1.4 G's if we want to remain straight and level in a level turn. So we bank it over to 60, it goes to 2. Just 10 more degrees to 70, and we add another additional G. We go up to 3. So we can see this is not linear. This is an exponential type relationship here. 80, we add another 1.5. It's even increasing even further. Why is this important? Okay, because in our aircraft, we have load factor limits. That's G's, right? So, why do we care about this? Because per our POH, Pilot Operating Handbook, our aircraft has certain limits. And again, if I'm writing the wrong limits, please write the limits down for your plane. Cessna and Archer may be a little different. They should, typically, this is the normal range for a normal category, general aviation aircraft. So, positive 3.8, negative 1.5 Gs. Why is this important? Because if we exceed 3.8, what the manufacturer's telling us is the plane is trying to handle 3.8 times the force of gravity, okay, or weight, right, that we are imposing on these wings. So at some point, the wings can't handle any more stress. And this is the limit that the manufacturer has determined for our aircraft. So if we throw our plane into an 80-degree bank and experience a 4.5-degree G turn, most likely we will come out of that turn without our wings. Okay, so it's pretty important that we know this stuff. Anything that exceeds a load factor limit of the operating handbook can cause structural damage and or actual breaking apart of the aircraft in flight, okay? So this is typically where I leave it. I don't really go much further than this, and some people say, well, you can't do this and not do VA. And so I have some people who are real gamers, and they want to do VA, and I'm like, fine, throw VA in there. You know what I mean? Make your lesson a little extra special, because from here, you can explain why, you know, the whole thing, and with you're closer to, when you're heavier, you're closer to the angle of attack, and it will stall sooner, all that kind of stuff, right? You get into that in the VA chart and everything. I think this is good enough. I've had everybody go through, with doing a lesson like this, or actually even less than this, and I've never had one complaint from any of the VPs saying that the lesson's not complete in any manner. So, but if you wanna load on and go for VA as well, dig that hole, baby. Game on. So, all right, cool. Any questions about weight and load factor? Oh, boy.
It's probably the same thing, but just for the G500
Yeah,
Archer,
that's
it's not approved for negative negative load factor limit.
Right.
So do we even mention it then?
Well, and again, we had this discussion
Yes.
the other day.
That's what I was gonna
Okay.
ask, would you put 0 then, and then 3.8, cause it has the positive, it just doesn't have a negative.
It did in the POH though, it
For
did.
G1000.
That's just for
Yeah, I
G1000.
showed-
We figured it out.
Oh, is that what it was? It was a G500 versus a G1000?
Yeah, I showed you the G1000 and it has the negative 1.5, but
Okay,
those doesn't.
but it
Yeah.
has literally 0?
It
Doesn't
doesn't
even
say
say 0,
anything.
it just says monthly.
Yeah, like, we pulled it up and it under.
Well, then I would put 0.
0, okay. That's
For
what
negative, I
meant.
would still put negative 0.
Yeah,
Okay.
Can't experience a negative G,
Okay.
which is, that's rough.
Yeah.
Cause even if you don't mean to, I mean, if you get a gust from underneath, it's gonna be a negative G.
Yeah.
Some amount of force.
Pretty sure it says not recommended in there either.
What's that? Oh, the
Negative
negative
limits?
Negative limits, yeah.
I think it's just.
Yeah, planes do not like to be stressed in a negative G fashion. You know, that's why even, you look at fighter jets, they roll onto their back before they don't dive and push over on the nose into a negative G dive. They'll roll onto their back and they'll pull positive G, right? Because you can pull a lot more positive Gs than you can negative Gs. Okay. Wait. All right. Thrust. Okay. Thrust that opposes drag. Propeller, we want to talk about that. Engine. 180 horsepower, 4-cylinder, horizontally opposed. You know, whatever you wanna talk about, but you should have some sort of little premise in the beginning of this. Just don't be like, thrust, turning tendencies. You know, I have a lot of people who jump in and they're like, weight, load factor. I'm like, well, what about weight? What about thrust? You have nothing on thrust? Nope, just turning tendencies. Like that's the PTS item, and you have to cover that, but you also have to make a little bit of a effort to make a slightly rounded lesson. So, you know, we're gonna talk about the propeller, and I'm gonna describe that to you, how I go into that, right? And then the engine, like you say, 4-cylinder, you know, naturally aspirated, or whether it's fuel injected or carbureted, you know, you can go into a couple different things, you know. And this is, you know, this is brake horsepower, and it's only at 15 degrees C on a standard day, right? At 2,992 at 2,700 RPM. You know, all the conditions are in your POH. What gives you that horsepower? Okay, for Lasky, if you have Lasky, he may ask you, he may say, what is the 4 conditions required for maximum horsepower? And I've had people look at me like, they're like looking cross-eyed at him, like, they're like, I don't understand what he's asking me. Like, he's asking me what's in the POH. So you're telling him you have a 180 horsepower engine. He wants to know, you know, if this was in, where's my Denver folks, right? You know, up at 5,000 feet, pressure altitude, it doesn't quite produce 180 horsepower, does it? Right? So what are the conditions for maximum horsepower? Sea level, standard pressure, standard temperature, and a given RPM setting. That gives you your max horsepower.
Would you consider that like a limitation? I don't know if that's part of the limitation section in the POH, but would you consider whether to be a limitation for the engine?
The engine, like the
Yeah.
horsepower, that would be a limitation. That's the maximum horsepower that your engine can produce. So that would be a limitation, if you will.
Okay.
a performance limitation at least, right? But how much it can produce. So, yeah, so any Ulaski folks, don't let him trip you up on what are the 4 things that cause maximum, or, drive maximum horsepower from your aircraft. It's those 4 things. It's really simple. He's asking you an easy question. It's just that the way he asks it, it seems really like he's asking something very difficult sometimes. And he doesn't mean to. He's relatively, he's a nice guy. He likes to teach, and if he sees that you know what you're doing, he's more likely to teach you the rest of the lesson and have you teach the complete lesson. So that's how it sort of goes with him. But he's got to get that feeling that you know what you're doing first. If you struggle at all, he'll go back. He'll go to being a normal DPE, and he'll start digging and needling just like any of them will. So okay. So the thrust, talk about the propeller, and the propeller I talk about like why from the propeller, why. Have you ever wondered why an airplane propeller is twisted? Why don't we just have 2 straight arms out there? You know what I mean? Why does it have this weird, if you look down to the side of it, it kind of has this like weird shape, right? It has something that's called, the actual name of it is called aerodynamic twisting. Okay, that's done to our propeller, the shape. It gives us the shape of our propeller. So our propeller is really 2 airfoils, if you will, in the vertical position, and it creates horizontal lift, right? And that horizontal, like a fan, right? And that horizontal lift, fan is what we consider thrust. So, why is it twisted? Because, let's see here. So this is a solid unit, right? So just like as if I had a person standing here. Again, we had people on a rope. And these people are ice skating. Okay, this is on an ice skating rink of some sort. Stay in the ring when they do this. So this person is just gonna basically spin around. That person in the middle is like the anchor for all these people, and everybody else is at a certain length away from this person holding on to this rope, okay? But they all have to move together in a line. That's their job, right? So they move together, they move around in a line, all these people. But the thing is this person, all he has to do is just turn around. This person pretty much can just, almost just glide, right? This person's skating, and this person has to skate fast, right? Makes sense why, right? Because this person has the greatest distance to go on the outside, right? This person has 0 distance really to go to here. They're literally just spinning around. So if they have a greater distance to go to in order to stay in a line, the further we go away, the greater the distance around, the further we go away, the more that person has to run or skate faster and faster and faster in order to stay in line with all the other folks. So here, kind of the same thing. We have low velocity on the inside of our propeller, and we have a very high velocity on the outside of the propeller blade, spinning around there. And so, if our airfoil was constant all the way across, kind of like our wing, it wasn't twisted, it was more of a form of our wing, it was just straight, right? What would happen is, we would experience different velocities of relative airflows over the propeller, right? So the air would be moved, this part of the propeller would be moving very fast through the wind, this portion would be moving very slow. And we know from Bernoulli's principle that if that's the case, that means that the outside here would generate a lot of lift, and the inside would generate very little lift. But what the engineers have done, they've come up with, is they've twisted the prop, the propeller, such that we have a very high angle of attack on the inside of the blade and a very low angle of attack on the outside of the blade, which is the other way in which we generate lift, right? Angle of attack. Velocity and angle of attack, Bernoulli and Newton, comes back to them again. So, the whole idea, or why is it twisted? It's so that we have constant lift, okay, across the entire blade of the propeller. And how do we do that? Well, for that portion which has an increased high velocity, we compensate it with low angle of attack. And for that area which has a low velocity, we have a high angle of attack. And by compensating, because we can't compensate on velocity, this thing it all turns in at one time, right? It's a piece of metal. So the only way in which we can compensate for that difference in velocity from the hub out to the tip is to vary the angle of attack. And by doing so across that entire blade, by that high angle of attack going to a relatively low angle attack, okay? Out at the end, we're able to maintain, and this is the reason, is constant lift. So we can create constant lift. Otherwise, the outside of the blades, the tips, are gonna create a lot of lift. And so if we were spinning the blade really fast, the blade would just do this while we're flying. Our blades would be like, whoa, right? The outside would because the inside wouldn't be producing much lift, the outside would be producing a ton of lift. So it would actually, it would flex the blades or want to bend, the blade would want to bend on the outside forward from all the lift that it's, or thrust that it's producing. Okay, so that's one thing that you should talk about for sure when it comes to thrust. Propeller, shape, you can use the prop, if you have a model prop, you can use the little example, like the shadow example with the flashlight, and you turn it, right? So, and things like that. But yeah, it's good to have a model prop for sure. Did everybody get what they wanted from here? No? What's up?
I have a question.
Yep.
So kind of like the ice skating example that you were talking about, do you think like a tetherball example would be another good way to explain it as well?
If you have multiple tetherball, like if you have, well, tetherball's like one, or like is that like just a?
Yeah, so it's like one ball in the end, but like once it wraps up, it speeds up.
Oh, it speeds up.
Yeah, like so say you hit it and it starts wrapping around,
Mm-hmm.
and it generally gets faster as it gets closer to the center of the pool.
That's the opposite.
Yeah, that's a different.
Different kind of like philosophy sort of
Well,
thing.
yeah, it's a
Okay.
different, yeah. So what you would want is, you want something that's constant, that's not getting shorter, because obviously, like say, this one, if you're going fast and you're going a certain speed, again, it's a completely different concept, you know
Okay.
what I mean? But yeah,
Okay.
keep it like this. I've heard some people use like a track and field example, like runners. You know what I mean? Like, so the person, you know, on the outside, like if you're running on track and field, you have all the different lanes. It's like, well, what lane do you wanna be in? I wanna be on the inside lane. Why? Because I'm actually traveling, you know, the least amount of distance around the track than the person who would be on the outside lane, right? They actually have to run faster, you know, if they all started at the same spot, which is what we're doing. The reason the track and field doesn't is because they actually stagger the runners, so you kind of have to modify the track and field example a little bit to fit this, not maybe how it's done in real life to keep it competitively equal. You know, you have to kind of do it a little bit to fit your example. But the skaters or the whatever on a string that are going around a circle, that anything like that works fine.
Okay, thank you.
Sure. Alrighty. Oh, thought I got out of that already. I was gonna mark thrust complete. No. So, okay, so we have the propeller. So you're talking about the engine, then you're talking about the propeller and the design, and then basically the last thing after you talk about all that and twisting and everything else, they're like, you know, and so, you know, we do have the propeller, you know, that is the mechanical means in which we produce thrust for our aircraft. So we have some reactions from this type of thrust that's created, that creates some, if I could write today, turning tendencies in our aircraft. And so we have P factor, propeller factor, slip stream, and gyroscopic precession. And torque.
I see my Google Calendar, that is
Okay.
next week.
So P factor, I find this extremely hard to do on the board, almost impossible. But again, I think it's with the propeller blade, that's the best, where you have something like that, that's perfect. So, you know, P factor is, you know, basically the way our, if we look at a cross section of our blades, you know, how they're kind of mounted to our aircraft. That's sort of how it, something like that, right? So they look something like that, right? There's like, it's like literally like two airfoils that are sort of crossed like that, right? So when we're level, we're on the ground, we're in straight and level flight, anything. We have both blades, so we have the hub and we have blades that are kind of over here. We have the one blade that's ascending and we have the other blade that's descending, okay? And this is looking, so we kind of get an idea. There you go. Right, so it's looking out, it's looking at us, the plane's flying towards us. Elevator sticking out from behind, the rudder sticking up over the top of the canopy, so. So we have this relative motion in this direction. So we have a descending blade right, and an ascending blade on the left side of the aircraft. Okay, which I know it's weird, it's backwards, but it's reversed because it's coming at us. So the angle of these two blades in straight and level of these two blades are relatively equal. So most people are like, well, the descending blade takes more than the ascending blade. I'm like, well, when? They're like, well, always. I'm like, no, not exactly. When we're level, flying in straight and level, or when we're sitting on the ground, we're about to take off, there is no real turning tendency with the P factor, right? But it's when we pitch up, so at high pitch, and that could be positive or negative. Okay. Well, let's do one. High pitch. The descending blade is going to take a greater, this looks like crap, it's the same. Greater than this angle here, the ascending blade, and if we have a low pitch or negative, I should say positive, negative pitch, then this angle would be greater than, did I do that right? This angle is going to be, the descending, at a high pitch, the descending is going to be more. The descending blade is going to be more. I drew it backwards. The descending blade is going to be greater, right? Descending is going to be greater. Negative pitch, the ascending blade will be greater. So typically we talk about this in relatively high pitch attitudes. So if we have a high pitch attitude, what happens is the descending blade becomes very flat, like a paddleboard, and the ascending blade becomes more like a knife and just kind of slices through the air. It doesn't have a great angle of attack, right? One has a massive angle of attack, and the other one has a very low angle of attack. So it's at high angles of attack. Okay, descending blade, it's in a climb, it's a positive, has an increased angle of attack, and the ascending blade has a decreased, very much decreased angle of attack. And so if this is creating a lot more thrust over here on the descending blade, because we pitched up, it's going to give us a turning tendency to the left, right? It's going to yaw us to the left. So this will be a high angles of attack. It'll give us a left yawing tendency, or left turning tendency. And you can try and draw some of this stuff on the board. A lot of it, like I said, it is, that little prop is worth its weight in gold, because you just can kind of just show that and go, and look, when I tilt this up, look what happens, and that's it. And then you're good to go. All right, cool. All right, so I'm gonna erase this one, and then we're gonna go to, so that's P factor. So spiraling slipstream. So So spiraling slipstream talks about that your accelerated slipstream is off of our propeller, right? So there's additional airflow from that fan or from this propeller thrusting us forward and pushing that air behind us. And so that accelerated slipstream also creates a spiraling slipstream around our aircraft. Now, again, at high angles of attack, the left side would be generating a lot less thrust than the right side, and therefore, most of the air which is coming down the right side of that body ends up moving underneath our body, coming up around the left side of the fuselage and hitting our vertical stabilizer in the left side. So that causes a push in this direction and causes a yaw in that direction, right? So again, this would be a left turning tendency from the air hitting our vertical stabilizer on the left side from the spiraling slipstream that's generated from our accelerated slipstream from the propeller itself. And again, would be greatest at high angles of attack. Gyroscopic precession. This one real quick, gyroscopic precession. Let's do, I'll do gyroscopic precession last. Let's do torque. Okay, so torque. Actually, that's not right. Way too big of a plane. What's in there? All right, so let's just do that, and then we'll do this, here. Okay, something like that. Okay, you sort of get the idea. All right, so plane's coming at us. We know that, again, the propeller's always spinning in this direction. So anytime we have a spinning disc of any sort, that is a gyroscope in essence, and so it's going to act like a gyroscope. It's going to have the same, it's going to be governed by the, principle of rigidity in space, right? Just like any gyroscope. And one thing about a gyroscope, though, is that the actual resultant force is felt 90 degrees along the path of rotation from where it's actually applied. Okay, it's felt 90 degrees along the path of rotation, further along than where the force is applied. So, when do we typically apply gyroscopic force to this? Well, we do it when we pitch our aircraft up or down, okay? That's going to move that disc. That's going to basically take that disc that's spinning out in front of us there, and we're either going to be moving it, pitching it in upward direction, or pitching it in downward direction. Now, only while the time that the pitching moment is occurring do we have gyroscopic precession. So, during pitching moment. And what do I mean by pitching moment? When the pitching is actually occurring. Okay, so in other words, if I'm a straight and level and I pitch to 15 degrees nose up, as I'm pitching to 15 degrees nose up, that's the moment itself. So I'm feeling gyroscopic precession. But if I get to 15 degrees pitch up and I just maintain 15 degrees pitch up, I'm able to just do that and just fly 15 degrees pitch up. I have no more tilting. Now I'm at a constant again. It's 15 degrees pitch up, but it's still a constant. There's no more gyroscopic precession being felt. So it's only during the pitching moment, I guess I would say another way would be the transition Does that make sense? So when you're actually moving, that's like, you know, so if you ever grab that bicycle wheel and you, maybe if you had that physics class or anything like that, that's, you actually have to move it. It has to be during the movement period, transition period, that you'll feel that precession. So, basically we have two types, well, it's one type of precession, but we have two instances, for, wait a minute. I was talking about torque and then I went into gyroscopic precession. I confused myself.
Yeah.
Dang. I said, let's go to torque, and I started talking about gyroscopic precession. I'm sorry. I'm combining the two. All right. Somebody stop me. All right. Well, you know what? Let's just talk, I'm just gonna continue on with gyroscopic precession since I started. Let's just finish that out, since I'm already halfway through it. All right, so gyroscopic precession, pitching moment, transition period. It's when you're actually doing that. So, when you are, so we have two different types of gear. We have conventional gear and we have tricycle gear, right? So it's typically explained, these gyroscopic on takeoff is when we kind of feel them the most, okay? Again, because we're going from 0 power to full power, we have relatively less authority on our flight controls because the airflow's low, so, right, we don't have good authority. We get a lot of feeling of this gyroscopic precession on takeoff, or effect from it. So, if I was a tail dragger, the first thing a tail dragger needs to do is they need to pitch down, right? Because they're sitting like this, like a hoopty, right? You see those trucks going down the road, right? All jacked up in the front down here. And so the first thing they have to do is they actually have to push forward on the stick to get that tail wheel off so that they're just on the mains before then they lift off and they pull up, right? So if this is the spinning disc, if you will, if it's pitched upward, and so I'm applying a force, I'm actually going to push or transition this to more of a straight level rather than upward attitude, I'm going to be pushing that top forward, right? We're down, seems down, but it's forward. So as I'm pushing that forward, it's spinning, if we're sitting in the cockpit, this direction to the right. And so even though I'm pushing here, it's not felt here. The force is felt 90 degrees along the rotation of the path, which means it would be felt over here, still pushing outward in the same direction. So if I have this, and let me see, I'm just trying to see which way to draw this will be best. So probably this way. Okay. So if I have a tail dragger, this is a tail dragger, and I'm pushing forward, I'm applying a force to the top of the blade. Obviously I can't draw 3D on a 2D board. I have to make multiple drawings to do this. But that is felt 90 degrees. So it's applied here at the top, but it's felt here over to the right. Because the blade is spinning from, if it's at top dead center and you're looking in the cockpit, where does the blade go? It goes this way, right? So it's felt to the right. So therefore, it's going to feel as though it's a yaw to the left, if you will, or that force is going to act, it's going to push hard from the right side, yawing our aircraft to the left. So that's gonna create, again, another yaw to the left. Okay, well, what about our tricycle gear? Or tricycle gear, we don't do that. We're already level. The first thing we do is we get up to speed and we pitch up. So if we pitch up, we're actually pushing on the bottom of that blade, right? So the bottom of that blade is spinning around. And so, let me think. Am I thinking that right? Or I have that backwards? Right, pushing on that,
It's right.
Yeah,
this,
it's a right turning tendency.
because it's a right turning tendency, right? Yeah, so if we do that, it would spin to the left, and that would actually be a left turning tendency. So on our tricycle gears, it's a left turning tendency. So basically what we need to know about gyroscopic precession is if it's a negative pitching moment, it's gonna be a left tendency. It's gonna be a force to the left. And if it's a positive pitching moment or pitch up moment, it's gonna pitch us or it's gonna move us to the right. That's the end game of what you wanna get out of gyroscopic precession. But it's only felt during the transitionary period. That's the other thing too. So it's only momentary. As soon as you get that established, now it's gone. Okay, so we got gyroscopic precession out of the way. So torque, which was up here, it's basically, again, the propeller's spinning in the one direction. So literally what happens is it's Newton's third law again, equal and opposite reaction. If the blade's spinning this way, the plane actually wants to torque the other way. So you could figure this out if you ever used like a drill, and drills spin clockwise. So if I ever was drilling into something, and let's say that drill bit just stopped, it got hit on a rock or a knot in the wood or something like that, my hand would not spin clockwise. As soon as that bit stopped, it's gonna twist my hand counterclockwise. So if I was like Superman and I could go out there and grab a plane out of the air and just grab the propeller like this, that plane, and stop the propeller in an instant with my hand, the plane would literally spin on its longitudinal axis counterclockwise. It would spin the opposite direction of that propeller, okay? That's the force that torque's creating. So the torque is another Newtonian third law example. If we have the propeller spinning this direction, the torque is going to be opposite the direction of rotation, okay? Now, in the air, this is a left rolling tendency. But we're not always in the air. Sometimes we're on the ground. So do we experience this on the ground, this torque effect? We do. We actually do. But it is no longer a rolling tendency. At least we hope it's not a rolling tendency because you don't want to ground roll. That's bad, right? So in this case, this torque is still, force is still going this direction, still applying, if you will, a force that's moving in this direction. So that force is being felt, if you kind of bring that down, it's being felt here. Okay, there's the force is applied to our left main gear. Okay, so if I add a lot of weight to one area of my car, let's say the trunk of my car, I could do it the left side of the back, the trunk of my car, right? So I get one side of my truck or car kind of really loaded down. What's that gonna do to that tire? What's it gonna feel? It's it's gonna feel more drag, right? So force applied on a tire is going to, so we're gonna have an increased force on this tire, which is going to increase drag. Okay, so, because it's being pushed harder into the pavement. So, if I increase the drag, that means this one is gonna go relatively, right? It's gonna spin faster, and this one's gonna wanna spin slower as a wheel, right? And if this wheel spins faster, just like a tank, one tread moves faster than the other tread that's on tank's turn, right? Variation of speed and treads on the left and the right side of the tank. So our right side's moving faster. It's going to be again, this is going to be a left turning tendency on the ground. It's a left rolling tendency in the air, but it's a left turning tendency on the ground because the ground's in our way. So that's that one, and that one, and thrust. Now I gotta do is talk about stability. How we doing time-wise? Oof.
Might be your record.
I might. We're getting close. What I started was like was it like closer to 2:30?
2:15,
Somewhere in there, right? It'll be close. 3, 4, 5. Yeah, I mean, it's about there, no matter what. I mean, I'm not moving at a slow pace. I'm moving at a decent pace, trying to give you guys time to copy and everything else, but still, 3 hours is typically what it takes you to give if somebody says, teach me all the principles of flight, it's 3 hours. Okay. All right. Stability. We have 2 types of stability. Static. And then we have static and dynamic stability. Static stability is the initial reaction to a disturbance of an object, its initial response. Okay, so we're talking about the very initial response. So I like the cup example. A lot of people like the graph examples on both. I'm a diehard bowl or cup example for the static. I don't know why. I just like it. So you can do it either way. It doesn't matter. They both work. But if I had a marble in the bottom of a glass or bowl or something like that, and I took that marble and I picked it up, I disturbed it, and I held it up here to the top of the side, one of the sides of the cup, and I just let it go. Well, based on the fact of gravity acting on that ball, it's going to want to return back to equilibrium back here in the center. Its initial reaction is going to be to go back down towards that. Now, obviously, it's not just going to do that. It's going to go down. It's going to go up over this side, and that's dynamic, right? If we kind of go back and forth, right? So, but static is just that initial tendency. Actually, you know what, the dynamic, I don't know if that, I'll do the graph for the dynamic. We'll do one of each. The negative, if I have a marble and I I flip that cup upside down and it's rounded on the bottom, and I just even give it a little bit of a push, its initial reaction is not gonna be to come back to the top of the cup, it's gonna be to continue down the side of that cup until it hits the ground, probably outside, right? So its initial reaction is gonna be to move further away. If something moves further away from its point of origin or equilibrium, that's negative static stability. And if I push a marble on a flat surface, it's gonna move so far depending on the amount of force that I apply to that marble. But once it's done rolling, it's just gonna stop if it's perfectly level, right? And so it's going to be displaced to a new place, a new placement, if you will. But after that, there's not gonna be any further movement either back towards the point of equilibrium or further away. It's just gonna get to a certain point away from its origin, and then it's just going to stop. For dynamic, well, actually, I guess the first thing we need to talk about is how do we get dynamic stability? So dynamic stability is the ability of an object to return to equilibrium over time, okay? And so we can't have any type of equilibrium at all in either of these two cases, in negative or neutral, right? Because they never return to equilibrium. The only way in which we can achieve dynamic stability is if we have something that wants to at least initially return to its state of equilibrium, and that's to have positive stability. So dynamic stability, this requires positive static stability. Without that, you cannot have dynamic stability. That was horrible. All right. So, and again, I'm sure all you guys, I mean, the point that I really need to teach you is after this is the three axes, but I'm sure you get this. Some people don't understand that you need, or they forget to mention that you need positive static stability to get dynamic stability. So make sure you mention it. It's very important that they understand, that you understand that concept. And then, so obviously this is over time. These are the graphs, positive. If there's a disturbance, it gets less and less over time until it returns to equilibrium. Negative dynamic stability is it tries to return, but it never can. It gets worse and worse with each attempt. And then negative is basically a perfect sine wave where it starts and it just never ends, right? It never gets closer, never gets further away. It just continues that equal oscillation on both sides of the of equilibrium. So that's your general discussion on static and on stability, static dynamic, okay? Anybody need anything from that or questions? No? Okay. Cool. All right. Then we have stability around the three axes. We have longitudinal, lateral, and okay. So let's talk about longitudinal stability. This one any better? All right. So Okay, so. So we have, longitudinal stability. So this is around the lateral axis, right? And so literally we have our center of lift acting in a positive direction. We have our center of gravity acting in a negative direction. And we have something back here. Something called tail down force. So, looking at our plane from the side, we have a couple things going on. We have our center of lift, which is just above, slightly forward in the center of our wing. Our center of gravity is typically up around our firewall, and sometimes like in your archers, it's like, the datum line at least is like out on like the spinner. It's way out there, very nose heavy. And then we have a new term here, tail down force. So what is this tail down force we speak of? Tail down force is created by our horizontal stabilizer, or whatever whichever one you have, right? We got different ones. So, and the way it's created is basically our elevators and horizontal stabilizer there create lift in a downward motion. So it's an upside down wing. So just like a wing is susceptible, just all the forces of lift, the Newton's third law, as well as the Bernoullian principle of velocity, increase in velocity or decrease in velocity is going to increase or decrease lift. Well, if we increase or decrease velocity, we're going to have an increase or decrease in tail down force. Okay, so center of lift is basically like our fulcrum. I always think about this like a teeter-totter. And so I've got CG out here on the one end, I got tail down force down over here on the other end. And as long as those two things are equal, then I'm able to stay balanced on that scale. It's when one of these changes that we, well, you'll see here in a minute. So we have a couple constants. Center of gravity. We get our center of gravity through what? Basically, that's where all of our weight is concentrated around, right? For our purposes of balancing, right? So that's the point where we balance at that point. By our weight. So, yes, our weight changes as we fly over time, right? We're eating fuel more than anything. So, decrease fuel, decrease weight. But in any 5-minute or span of time, how much fuel do we eat? How much weight does it vary? Not much, right? So over any one instance in time that we're talking about, I'm basically going to say that our center of gravity and our weight is relatively fixed. Our center of lift, does that change? Well, it does, depending on, again, just like we discussed, how fast we're flying, angle of attack, right? There's different things that control lift. But it really doesn't matter in this example here for our our longitudinal stability, because our center of lift is literally our fulcrum. It's what everything is actually operating around. So the thing that changes here is the tail down force. Okay, so this changes with velocity, right? Just like the wing. Increase velocity, increase lift, decrease velocity, decrease lift. So if I drew my little plane dynamic stability line, and we're cruising at 100 knots. Okay? And there's a disturbance that comes and pushes the aircraft up into the air, an updraft. So the aircraft kind of goes up this way. What's gonna happen when the aircraft gets to wherever it's gonna go to up the top there, or however much altitude we're gonna gain?
Is it a positive dynamic?
So it does. It does have positive dynamic, but I guess my question is, if we did nothing, the plane was just there, or you were sitting inside the plane and your arms are crossed and this just happened, so there's no intervention from the pilot, and the plane started going up, you didn't change power setting or anything, what is the plane going to do?
Decreases.
Airspeed's going to decrease, right? You would agree with that? So our airspeed's gonna go down to probably about 90 knots. Okay, let's just, or even we could do a little more. So we can do a couple things here. So we'll do 80. Okay, so 80. So 80, at 80 knots, is our tail down force more or less at 80 knots?
Less.
Less. So if our tail down force decreases because our speed decreases, which is what we said here, change of velocity, right? So if that tail down force decreases, that means the tail's gonna be allowed to rise up, and the CG is gonna take over and pull our nose back down, right? And so here it's gonna get to maybe 110 knots. At 110 knots, we have an increased tail down force beyond equilibrium, right? Because now we're faster, so if we're faster, again, this is, it increases with velocity and it decreases with velocity. And so if we do that, that's gonna push the tail down, and the nose is gonna come back up. And so we'll get something like this, until eventually, you get 110, maybe, I don't know, 95, and then somewhere around here we get 100 knots again. Just like the positive dynamic line graph chart, right? Same thing. And it all has to do with tail down force. It has to do with the fact that it's an upside down wing, which varies, and the force varies directly with velocity, just like our wing, So faster we fly, the more tail down force, the slower it flies, less tail down force, and that's what keeps it having that positive dynamic stability. That's the hardest one. If you can explain that, you've pretty much got stability. Because the other two are easy, like simple. So, everybody got what they need on this? Yep, okay. So, lateral stability. Talk about dihedral. D-R-A-L. Dihedral, something like that. Okay, I'm not a good great speller. All right, so we got the relative wind. So when it comes to lateral stability or along the longitudinal axis, we have dihedral. So this is tail down force. This is dihedral. And what's the other one? What's it called? The keel effect. And this is weathering. So if our plane gets disturbed and it goes into a bank because of this disturbance, what's gonna happen is, it's going to end up, especially if it banks enough, the plane's going to end up slipping off in the direction in which it banked, or in the direction of the lower wing. It's gonna slide off, okay, or slip off. And so when that happens, our relative wind is no longer coming directly at the plane. It's still coming at the plane, but now it's coming from the side angle because the plane is now slipping and moving forward at the same time, okay? So what that does is it shifts that relative wind, and you can see here, there's a certain angle, but you can see here that there's a much bigger angle. Those green lines represent the angle of attack because of that dihedral that's built into the wing that occurs when we go into the side slip condition when the aircraft is disturbed. So what happens is we have a greater, on the lower wing, we end up with a greater angle of attack on that wing, which means we have increased lift on that wing. And therefore the plane will have a tendency to right itself based on that fact alone. Based on the fact that we had the dihedral of this aircraft is built, and we have it specifically for that reason, for stability. You want to be less stable and have more controllability, take out the dihedral. Just have a flat wing, no dihedral. Then you can have aerobatic. The keel effect is more for our high wing folks. Again, this is something you could, so it's where basically the weight is concentrated mainly in the fuselage of our aircraft there. And so just like one of those like metal balls that you would pick up, or you know, and if you I'm trying to say this, let's see if that's the right example for that one. It's basically the keel effect, so this is keel effect. It's because of the force of gravity, right? So gravity is always pulling straight down to the center of the earth. So if we bank that aircraft and we throw the weight over off to the side here, we bank that aircraft, gravity, of course, is just going to want to pull it back to equilibrium, or the center, right? By itself, just kind of like those marbles or whatever. If I pick it up, it's going to want to go back down. That would also be an example of keel effect. You know, it's basically you're taking that force and you're taking weight, or the center of that weight, and you're moving it out from underneath the center. Well, gravity's not going to like that. So if it's undisturbed, we have that dihedral acting. We also have the weight itself wanting to shift back to be in center and equilibrium, right? Caused by gravity. So it's the dihedral and the keel effect combined that causes and gives us our lateral stability. And the vertical, so simple, right? Just basically have a plane, and so we have, you know, it's flying straight along, and all of a sudden we get yawed to the side. Well, the relative wind, because we're still moving, still slipping this way, so what's going to happen is this wind is going to end up hitting off this vertical stabilizer and therefore pushing the tail end of our plane this way and yawing us back in the direction that we wanna go. And that effect itself is just, you know, just like on top of a barn or anything like that, if you've ever seen a weather vane, right? It basically, that vertical stabilizer, or some people call it like feathers on an arrow, where it's there to stabilize and basically to weather vane it'll weather vane into the wind because of that. It's the weather vane effect. And that's it, sort of anticlimactic after longitudinal stability, you know, you tilt down for stall, this, and gravity, this, physics, this is just weather vane. So, that's all I got. So that's stability. So, cool. Hopefully these guys got something out of it.
Thank you.
Thank you.
You're welcome.
Thank you.
And look at that. Just in under 3 hours. Time.